Okay, so let's look now at our next topic, which is the atoms and the elements. So the learning objectives for this unit are understanding that atoms consist of a central nucleus composed of protons and neutrons, surrounded by subatomic particles known as electrons, which orbit the shells. We're going to be able to state the relative charges and masses of these subatomic particles, define atomic number, mass number, and relative atomic mass, define isotopes, calculate the relative atomic mass of an element from the relative abundance of an isotope, use the proton number or atomic number, which is also called, and simple structure of an atom to explain the periodic table, and deduce electron configurations of at least the first 20 elements from their position, and deduce the number of outer electrons in a main group from, again, its position in the periodic table. And finally, describe the buildup of electrons in atoms and the significance of full outer shells. So we're now going to look at the structure of the atom. So here is the structure we use, the model. Okay, so in the structure of the atom we're going to use in GCSE Chemistry, all matter is composed of atoms, and it's basically made of three different subatomic particles: the proton, the neutron, and the electron. Okay, and the protons and neutrons are present in a place in the center of the atom called the nucleus, which I've circled there, and the electrons are going to orbit around them. Okay, so these guys here are your electrons orbiting around the central nucleus, which contains the protons and the neutrons. So in terms of the relative mass and relative charge, we don't necessarily have to worry about the charge and mass for this level of chemistry, but we do have to look at the relative mass and relative charge of each. So protons, they are relatively heavy, so they have a relative mass of 1, hence they're in the nucleus. They have a relative charge of +1. Say protons are positive, both P. Neutrons are neutral, so they have no charge or 0 charge. Okay, 0 charge. And they have a relative mass of 1 as well. And electrons are essentially have a mass of 0, and they have a negative charge of -1. So when you look at the periodic table, you have to be able to interpret the chemical symbol. Okay, so the atomic number, also known as the proton number, is the number of protons in the nucleus. It tells you what the element is. So every atom of oxygen has 8 protons. Every atom of carbon has 6 protons. Every atom of hydrogen has 1 proton. The mass number, also known as the nucleon number, tells you the number of protons and neutrons in the nucleus, because that's where the mass of the atom comes from. It's the top number. So in terms of calculating numbers and of subatomic particles, we can calculate the number of subatomic particles if we have the atomic number or proton number or the mass/nucleon number. Okay, so that will be given to you in test or exams. The atomic number or proton number and the mass or nucleon number can be calculated for any element if the number of subatomic particles is known, because we know that the atomic or proton number equals the number of protons, the mass or nucleon number equals the number of protons plus the number of neutrons, and because of the calculations, we can work out the number of neutrons because it's going to be the mass number minus the atomic number, that top number minus the bottom number. And also, an atom does not have any charge, so we know that the number of positive charges equals the number of negative charges, so the number of protons will equal the number of electrons. If we know the proton number, we can work out the number of electrons. Okay, so for oxygen, we know the proton number is going to be 8, so it's going to have 8 electrons. Okay, because number of electrons equals number of protons. So here is an example that I want you to do. Uranium-235. Work out from the numbers given what the number of protons, neutrons, and electrons are. Okay, so this is how we do it. So from the data we've been given, we know that the mass number or nucleon number is 235 and the atomic/proton number is 92. So from that, we now know that the number of protons equals the atomic number. So therefore, the number of protons in uranium is 92. Every atom of uranium has 92 protons. We also know that since the number of electrons equals the number of protons, then the number of electrons in uranium is going to also be 92. And as we know, the mass number equals the number of protons plus neutrons, and the atomic number equals the number of protons. We can therefore work out the number of neutrons is going to be the mass number, 235, minus the atomic number, 92. So number of neutrons will equal 143. Okay, so uranium is an interesting example too because it's an example of an isotope. So all atoms of a particular element have the same number of protons and electrons. Okay, so every atom of uranium has 92 protons and also 92 electrons. And the proton number determines the chemical properties of an atom. However, the number of neutrons may vary within the atoms of an element. And this is called an isotope. Okay, so atoms of an element have the same number of protons, but they can have different numbers of neutrons, so therefore different mass numbers. So in other words, atoms of the same element with the same proton number can have different nucleon numbers or different mass numbers, and we call them isotopes of that element. So let's look at carbon. The proton number of carbon is 6, so every atom of carbon contains 6 protons. All carbon atoms have the same atomic number, but their nucleon number can be different, their mass number can be different. Okay, so you can have carbon atoms that all have 6 protons, but some have 6 neutrons, and that would be known as carbon 12, okay, mass number of 12. However, some carbon atoms also have 6 neutrons, some have 7, and some have 8. So it gives mass numbers of 13 and 14. So you have 12 carbon, 13 carbon, and 14 carbon, which are all isotopes of carbon. Okay, here they are in images. So you have 3 different isotopes of carbon. Carbon 12, which has 6 protons and 6 neutrons in the nucleus. Carbon 13 has 6 protons and 7 neutrons in the nucleus. And carbon 14 has 6 protons and 8 neutrons. Okay, so you'll notice that the mass number is going to be the sum of these 2 numbers. So how do we use isotopes? Well, carbon 14 is special as it's radioactive. Not all isotopes are radioactive. That means the atom is unstable and releases something called radiation as it breaks down. We call these guys radioisotopes. Most natural isotopes are not radioactive. However, we can use radioactive isotopes because they're quite useful, especially in medicine. Some are used to check leaks for traces. Some are used in radiotherapy to treat cancer. Some sterilize objects like medical instruments, so the germs aren't there, so we don't get infected if we use them. And some we can detect, for example, if you've got a bump in your spine which you need to be treated by a doctor. Okay. Another important thing is that you'll notice on the periodic table at the back of the class is that the masses are not perfect whole numbers. They are known as relative atomic mass. They are a ratio, essentially, of all the different isotopes. Okay, so the relative atomic mass of an element, AR, is the average value of all the isotopes in the element. Okay, so if you look at carbon, for example, it's not carbon 12, it's actually carbon 12.01, because it's a ratio of all the different isotopes. The most common one, of course, being carbon 12, that's why it's closest to 12. So here's the example here. So carbon 12, most of the carbon in the universe is carbon 12, about 99%, about 1% is carbon 13, and about 0.01% is going to be carbon 14. So we add those together to give an atomic weight of roughly 12.01, okay, which is what we've seen here in the words in the diagram. Okay, so that means for every 100 carbon atoms, 99 will be 12 carbon, about 1 will be 13, and about 0.1 will be 14 carbon. Quite rare. Okay, so we just add them up, and then we divide them by 100 to get your average, which is going to be 12.01. So we also have to look at how the electrons are arranged. Okay, this is the electron configuration for the first 20 elements, which you have to get used to. Now you'll notice that basically there's shells outside the nucleus, okay, and the number of electrons, of course, equals the number of protons. There is always 2 in the first shell, okay. There's a maximum of 8 in the second shell and a maximum of 8 in the third shell. Now obviously as we go on, that is going to also be a maximum of 8, but you'll learn more about that later in chemistry. May not be 8. Okay, so explain this. Electrons build up around the nucleus in shells, as we saw in the earlier diagram of electrons. Okay, the outer shells are known as valence electrons. That's where the chemistry happens. It's kind of the sharing or moving around of those electrons in which chemistry is based upon. So the maximum number of 2 electrons in the first shell, and then 8 in the corresponding cell. So we're basically filling up. First it's 2, then we start filling up the second shell until that's full of 8, and then we fill up the third shell until that's full of 8, and we continue on going on like that. Okay, so unreactive elements either have 2 electrons or 8 electrons in their outer shells. They're full. Okay, and these guys are called the noble gases. Okay, they're group 8, which we'll learn about in groups and periods in the next slide. Okay, so here's the examples here of the noble gases. So as we move along, you can see that you're increasing the number of shells. Okay, 2 in the first one, maximum of 8 in the second, maximum of 8 in the third, and so on. Okay, and they're unreactive because their valence shells are full. Okay, so now we're going to look at the periodic table in a bit more detail and look at something called groups and periods. Okay, so the periods are the ones that are going across. Okay, they're known as the periods. So a period is a row of elements in the periodic table. All the elements in the period have the same number of electron shells, but you're increasing the proton number by 1 by every element you're going across. Okay, so you've got hydrogen in group 1, in period 1, and then also in period 1 is helium, which has now 2 protons. Lithium, okay, same again, you've got 3 electrons, 3 protons. Next one is boron, 4. Okay, but the proton number, so basically proton number is increasing as you go across. So for example, every element in the top row, the first period, has 1 shell for its electrons. Okay, then we have the groups, which go down. Okay, and the groups are a column of elements in the periodic table, and the elements in this group all have very similar chemical and physical properties, which we'll learn about next in the next unit. Okay, because they have the same number of valence electrons, same number of electrons on the outside. Okay, for example, group 1 elements all have 1 valence electron, group 2 have 2, and so on. Okay, so these are actually labeled group 1, group 2, group 3, group 4, group 5, group 6, group 7, and finally group 8. These guys all got 1, group period 2, period 3, period 4, period 5, etc. as you go down.
As you move from the light elements to the heavy elements, you keep periodically coming across the same properties, which is why it's called the periodic table. The recurring properties are organized so that you can easily see similarities between elements. The periodic table is arranged in periods and groups, going from the light elements at the top to the heavy elements at the bottom. The rows going across from left to right are periods. Elements in the same period all share something in common. They have the same number of energy shells. Each new period row represents a new shell, Elements in the first period have one shell, and as we go down, the shells increase. Hydrogen is in the first period. It has one shell. Potassium is in the fourth period and has 4 energy shells, as do all the other elements in this period. The columns going down from top to bottom are the groups. Elements in the same group also have something in common. Elements in the same group have the same number of electrons in their outermost shell. The electrons in the outer shell are called the valence electrons. This just means that these are the electrons available for reactions and bond formation. The number of electrons in the outer shell governs elements' reactivity, which is why elements in the same group have similar properties. The group number can tell you how many electrons are in this shell. For example, let's look at group 7, fluorine, chlorine, iodine, bromine and acetine. They all have 7 electrons in their outermost shell and all exhibit similar chemical characteristics. The properties show a gradual change going down the group as we go from period to period. So if we look at group 7 again, we can see that they are each in a different period in the periodic table, telling us that each element in this group has its outer electrons on a different shell. So chlorine is in group 7, period 3. Therefore, it has 3 energy levels with 7 electrons in its outermost shell.